Hey everyone, welcome back. I am absolutely thrilled you're joining me today for another explainer. So, when you think of sculpting, you probably picture a hammer and a chisel delicately tapping away at a block of marble, right? Well, today we're going to look at the massive industrial equivalent of sculpting. Only instead of a tiny chisel, we're using a literal tornado of sharp edges to carve right through solid steel. We are demystifying metal milling and uncovering the incredible, invisible physics of precision that makes modern manufacturing even possible. Let's get into it.
Okay, here is our roadmap for today. We'll be covering milling basics and objectives, core metal shaping operations, selecting your milling machine, up versus down milling, and milling tool engagement, and finally, achieving precision and mastery.
Section 1, Milling Basics and Objectives, Setting the Foundation. So, picture the absolute star of the show here, a rotating cylindrical tool packed with multiple cutting edges. The whole foundation of milling comes down to one core concept, relative motion. You've got this aggressively spinning cutter, and you're feeding a workpiece right into it to carve away material. It's a continuous, highly dynamic process, literally slicing away solid metal bit by bit to hit a perfectly specific dimension. Now, why do we do it this way? Well, we have three massive goals we're trying to hit every single time. First, high production efficiency. Basically, we need to do this fast, but, speed just isn't enough on its own. Second, we absolutely have to maintain positional accuracy, specifically hitting what engineers call IT7 to IT9 tolerance grades. And third, surface roughness. We're aiming for a final finish somewhere between 1.6 and 12.5 micrometers. To put that into perspective, that is way, way thinner than a single human hair. So to sum it up, we need it fast, incredibly accurate, and perfectly smooth.
Moving on to Section 2, core metal shaping operations, sculpting the metal. The sheer versatility we have here is honestly incredible. Just by changing how the cutter is oriented against the metal, you get completely different results. On the simpler side of things, we can carve out basic flat horizontal surfaces using plane or slab milling, or make flat right-angled surfaces with face milling. But then, and this is where it gets really cool, we get into the advanced stuff. We can cut specific angles, completely irregular outlines, or if we use profile milling, we can actually reproduce the exact intricate outline of a complex master die. It's just such a flexible process. All right, Section 3, selecting your milling machine, the heavy lifters. To actually pull off these super precise cuts, we obviously need some serious hardware. Machine selection basically boils down to two things: spindle orientation and how much weight the machine can literally handle without bowing. You can see the architecture drastically change based on the job. Horizontal and vertical knee types are fantastic for small to medium parts. But when you need to mill something massive, that's when you graduate to the gantry-style planer type machines. They're built with these huge solid beds strictly for high load-bearing capacity. Let's put this physical capability into perspective for a second. If we look at the specs for a universal knee-type machine, you'll see it has a wildly versatile universal milling head, meaning you can easily swap between vertical and horizontal use. But check out that max weight specification right there, 500 kilograms. That means on this fairly standard machine, we can precisely mill a block of solid metal that weighs as much as an entire grand piano. Absolutely wild. Let's dive into Section 4, up versus down milling, the physics of the cut. Now we're getting right down to the actual point of contact, the high-stakes physics battle between the spinning cutter and the moving metal. There's a stark contrast between the two fundamental cutting strategies here, and it all revolves around feed direction. In up milling, which is also known as conventional milling, the cutter's rotation and the feed of the workpiece move in totally opposite directions. The cutter actually starts biting at zero thickness and works its way up to the maximum thickness. But with down milling, also known as climb milling, it's the exact opposite. The forces perfectly align in the same direction, striking right at maximum thickness first and tapering down to zero.
Because the physics involved are just so different, operators choose them for highly strategic reasons. Think about it. Down milling actually presses the part forcefully down onto the table. That makes it your absolute go-to for slender, thin plate parts that are usually a total nightmare to clamp securely. Up milling, on the other hand, cuts upward from underneath the already machined surface. Why does that matter? Because it protects your tool. It keeps the cutting edge from getting totally destroyed by hard surface crusts or impurities sitting on top of the raw, unmachined metal. You really have to be careful with this, though. Because down milling aligns the cutting force directly with the feed direction, it can actually cause the workbench to suddenly lurch forward if your clamping isn't completely rock solid. If your setup is even slightly less secure, or if you're working with materials that have good plasticity and toughness, then up milling is definitely your safest, most effective bet. It really is this delicate balancing act of physics.
Section 5. End milling tool engagement. Micro-level strategy. Let's stay at this microscopic level and look at a specific operation called end milling. Here, exactly where you align the center of the tool dictates the entire dynamic of the cut. If you align the center of the cutter perfectly with the center of the workpiece, you get symmetric milling. But you can also intentionally shift that cutter off-center. This creates what we call asymmetric climb or asymmetric conventional milling. This is where it gets truly fascinating. It shows exactly how a master operator manipulates physics on the fly. A perfectly symmetric cut gives you an exact 50-50 split of conventional and climb milling at the same time. But let's say you hit a tricky material, maybe something with really high toughness, or a metal that actually hardens the more you work it. You can intentionally shift to an asymmetric conventional offset to basically conquer that severe work hardening. You are literally altering the physics of the cut just by shifting the tool a few millimeters to the side. Mind-blowing, right? Finally, Section 6. Achieving precision and mastery, the human element. Let's zoom back out to the operator, because at the end of the day, all this incredible machinery and nuanced physics requires a master human mind to orchestrate it safely. As Dr. Sameh Tawfik points out in the material for today's explainer, true mastery isn't just knowing how to flip the switch on the machine. It's the rigorous procedural training. It's perfectly combining machine selection, knowing exactly when to use a universal over a planar, with a deep intuitive understanding of feed dynamics. Blending the right machine architecture with the optimal cutting physics is the only way an operator can safely achieve that ultra-precise IT7 to IT9 output we talked about earlier. So I want to leave you with one final thought today. Take a second to think about the smartphone, tablet, or monitor you're using to watch this explainer right now. Underneath the glass and the battery, the entire internal structure relies on these microscopic, exact metallic tolerances. How has this hidden world, the intense physics of up and down milling, those precise asymmetric offsets we just looked at, shaped the very technology sitting right in your hands? The truth is, the world of precise metal milling is everywhere, quietly holding our modern lives together. Thanks so much for learning with me today, and I'll catch you on the next explainer.